we have seen few relations. Those relations are based on basic thermodynamics. Now, those relations, let me note down all those relations one by one just to have a brushing. One is reaction isotherm, which is del Z 0 plus RT ln product, activity of product divided by, in the denominator it would be activity of reactant. So, this is a reaction isotherm, this is called reaction isotherm. Now, second relation which is coming from this is del G 0 in the standard state, which is basically 1 atmosphere pressure, and normally we consider at 25 degrees Celsius temperature. So, that case minus RT ln Ka. If we consider these things in activity, so it would be A, that subscript would be A. If you consider these things are in concentration unit or molarity unit, that case it would be C, and A is related to C in this way, and A equal to C for a very dilute solution or ideal case. So, that case K A equal to activity equal to concentration. Now, we have also come across redox reaction, and in case of redox reaction we have seen a Nernst equation which is valid, E equal to, and we have also considered the reduction potential, that case ox divided by red, that means oxidant goes to reductant, or the reduction process E0 ox red plus RT NF ln concentration of ox, concentration of red, or you can also put it in terms of activity of ox or activity of red, depending on the situation. If it is a very dilute solution, then activity of ox you can replace with the concentration. Now, this is the N factor that is coming because ox plus Ne equal to red. So, number of electrons that are associated with this reduction process is N. So, that N is coming, F is 1 Faraday for 1 gram equivalent substance to deposit or to come out in the solution in the form of ion. Now, again we have seen the relation between G del G and potential, reduction potential, which is del Z equal to minus NF E, or del G 0 equal to minus NF E 0. That means, if you consider standard state, then you replace this E in the form of E 0. Now, if you consider a potential difference of a cell, that case this E would be replaced by del E and this E would be replaced by del E 0 in case of cell. And in case of single electrode, that case this you put it as E. In fact, this in case of single electrode I am using E, single E, not del E, but still this has a meaning of del E, because you are measuring this potential in the with respect to one standard hydrogen electrode, where the reduction potential, standard reduction potential is considered to be 0. So, this is also a kind of del E for a single electrode. Now, with this equation we have also come across a triangle which for a particular reaction, and if it is a redox reaction, then we can have this triangle E0 cell, this is del Z 0 and this is K, which is the equilibrium constant. Now these are also related, like del Z0 equal to minus NF E0 cell, just like this, and this is del Z0 equal to minus RT K ln K, and this one is E0 cell equal to RT by NF ln K. You can put it Ka or Kc depending on whether you are considering activity or concentration. Now from this also you can also judge whether a process is spontaneous or not. If let us say you have del Z0, E0, these are the values which are considered, and have this is equilibrium constant, this is energy change in the standard state, this is potential in the standard reduction potential in the standard state, and when the activity of those species, ionic species, are considered to be 1. So that case E would be equal to E0, because we are considering this relation. If you consider this relation, when these activities of this redox, oxidant and reductant are 1, then E oxidation, E reduction potential of the electrode would be equal to E0. Now let us see whether a process is spontaneous or not. We can judge from this. Definitely, if it is negative, then it's spontaneous. We have seen. If it is 0, then it's equilibrium, and that means reactant and products are equally favored, and if it is positive, then this is non-spontaneous. That means the process, if this process, let us say reactant goes to product, see in this case whether this reactant would go to product phase or not, that would be decided according to this thermodynamics. Now similarly, you can also judge it from Kc. If it is greater than 1, if it is greater than 1, then this negative, this will be negative, because if it is greater than 1, because we have a relation del G equal to minus RT ln K, if K is positive and greater than 1, then this would become negative, and this is fulfilling the criteria. Similar way, this, if this is 1, then if this is 1, then this term would become 0. So del Z0 equal to 0. So it would be, again, this is considering equilibrium. So reactants and products both are equally possible. Now if it is less than 1, then this term would become negative, this term would become negative, and there is a negative sign. So this whole term would become positive. So if it is positive, so again the reaction is non-spontaneous. And how would you relate this E0? E0 again, if it is positive, from this relation, if it is positive, because del Z0 equal to NF E0 cell, if this is positive, so this becomes negative, this becomes negative. So again we have the spontaneous reaction. If this is equal to 0, so again this becomes 0, so it would be telling you the equilibrium condition. That means reactants as well as products both are possible. So that means that case this is going at a some rate, this is also coming back at some rate, or it considers a dynamic equilibrium condition. And if E0 negative or less than 0, that case this becomes positive. If del G0 becomes positive, so then the reaction is not possible, or it becomes non-spontaneous. So now let us have some numeric, some examples. If we see some examples, then things will be much, it would be more clear. Let us find out some, let us see some examples. Let us say if I would like to calculate, let us say zinc, okay. So zinc electrode, if it is immersed in zinc chloride solution, and in the zinc chloride solution the activity of zinc plus AZN plus 2 equal to 10 to the power minus 3, what would be the potential developed at this electrode? Okay. Now we know that E0 Zn plus plus Zn, that means for the reduction potential, standard reduction potential, when the temperature, the activities of those ionic species or other species are 1, that case E would be equal to E0. This is 0.761 volt. Now, we can have the Nernst equation E equal to Zn plus plus Zn. It would be always preferred to write this one in the subscript, because this will tell you whether you are taking potential in the form of reduction potential or oxidation potential. If you write in this manner, that means it always says that it's a reduction potential. If you write the reverse manner, let's say E Zn plus plus, that means Zn is going to Zn plus plus, this will tell you the oxidation potential. So I would always consider reduction potential, so I would always prefer to write this Zn plus plus Zn or ox slash red. Now this should be equal to E0 Zn plus plus Zn plus RT, the Nernst equation, and here if you consider the relation Zn plus 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 2E going to Zn, so that means we need 2 electrons for 1 mole of substance to deposit on zinc electrode from zinc ion. So now we have 2 electron, so 2F into Ln, ox is Zn plus plus. Here we are having the data in the form of activity, so activity of Zn plus plus and activity of Zn. Now Zn is in is in pure condition in metallic form, so this would be 1 and this value is 10 to the power minus 3. So now let me put those values, minus 0.761 plus, now at 25 degrees Celsius this T becomes 298 Kelvin, R is 8.31 joule, 314 joule per mole per Kelvin, and F is 96500 roughly 96, it's basically absolute, it's one F equal to 96500 coulomb per gram equivalent. Okay, so let me put those values, 2 into 96500 into Ln 10 to the power minus 3. So now if you calculate this, you would get the value would become minus 0.85 volt. So this is my voltage that would be developed on the electrode if you dip on zinc electrode in the zinc chloride solution and where the zinc ion concentration or the activity is 10 to the minus 3. This is one example. Now this way you can find out what would be the actual potential on the electrode if you are not at standard state, or if you are not maintaining the activity to be 1. So if the activities are different, then you can calculate from this Nernst equation. Now this is one example. Now let me have another example. This is little bit tricky. We will be using this concept just to find out whether a reaction is possible or not. Let me put all those values, R equal to 8.314 joule per mole per Kelvin, and T always we let us consider in 25 degrees Celsius or 298 Kelvin. Now the problem says that in a solution we have to find out, let's say nickel is corroding in a deaerated water. Deaerated water. I have a nickel plate which is trying to corrode deaerated water, and deaerated means the dissolved oxygen is absent. Okay. So now if you don't have dissolved oxygen, then you have some reaction, and it says that the pH of the solution is 8. These are given data. pH of the solution is 8, and Ksp, which is a solubility product, because when nickel corrodes, it forms nickel hydroxide. Nickel corrodes, that means it forms nickel hydroxide. So nickel hydroxide tries to precipitate out because its solubility is very less in deaerated water. So we need to find out what would be the solubility product of nickel hydroxide in deaerated solution. Its given data is given 1 in 0.6 10 to the power minus 16. These are the given data. Now another thing is, we know E0 nickel plus nickel is equal to minus 0.25. This is also obtained from reduction potential series, standard reduction potential series. The last class we have already started talking about what is the standard reduction potential series. After seeing this example, I would again consider the standard reduction potential series, and there we will consider what is the half cell and what is the full cell reaction. All sort of things will come into picture. Now again, now another data which is given as, now the reaction that are happening, of course nickel is going into nickel plus, and nickel plus is reacting with OH minus and forming NiOH precipitate. Now another reaction that is happening, one is nickel plus from nickel. This reaction is happening. If you have to have some corrosion of nickel, so nickel has to come as nickel ion, then it is basically a corrosion. So now we have 2 electron that is released by nickel to form nickel plus ion. So these 2 electrons should be consumed by some cathodic reaction or reduction reaction. The reduction reaction here, it is some hydrogen gas is forming. So if hydrogen gas is forming, so reduction reaction should be then H plus 2E equal to H2. So that means this reduction reaction is happening, this oxidation reaction is happening. So we have to find, the main question is, we need to find with this set of conditions, if the pH is 8, if the solubility product of NiOH whole 2, which is basically 1.68 10 to the minus 16, and the standard reduction potential of Ni plus Ni equal to minus 0.25, whether the nickel has any tendency to corrode in the solution, which is deaerated water. Now let us try to solve this. Now let me remove this. Now let us assume that nickel is actually corroding. So we have to find out theoretical of nickel to corrode in this solution. Fine. So now let us assume that this reaction is happening actually in the system, and this reaction is also happening. So if these are the 2 reactions, so in this case we have to find out what is the potential. Just like the previous example, we have to find out the potential which will be dependent on the nickel ion concentration in the solution. So for that we need to find out what is the nickel ion concentration in the solution. Same way we need to also find out what would be the potential for this, because this is also a reduction process. So that case also we can find out what is E for this, because here we are not maintaining the hydrogen ion activity to be 1, because we have already specified what is the pH. When activity is 1, that time pH would become, pH is mentioned as minus log of concentration of H plus. If we consider very dilute solution, then this is equivalent to activity. So when this becomes 1, so that time you can see that log of 1, so pH would become, so pH is defined as minus log of concentration of H plus. Now here we have considered pH to be 8. So if pH is 8, then hydrogen ion concentration is having some value, so you can put 8 equal to minus log H plus, so you can find H plus concentration in the media. So then also you will see that the concentration is not 1. So if these are not 1, so what would be the concentration of H plus ion, that we have to find out, as well as we have to find out what is the potential for this reaction if the species are not in unit concentration or activity, or same way like this we have to find out for this. Now let us find out these two, and one case, what would be E0 E of for Ni plus plus Ni. Though we are saying that this is going into the solution, but we can also consider in terms of reduction potential. So reduction potential for this reaction would be E0 Ni plus plus Ni plus RT. Now for this we involve 2 electron, so 2F Ln activity or concentration of nickel plus plus nickel, and this is pure state and in a metallic condition, so this would be 1. Now we know this relation. Now another case, which is E H plus H2 would be equal to E0 H plus H2 plus RT F, because in this case you can consider, you can write in terms of H plus plus E equal to H, and if that case it would be concentration of H plus and concentration of H. Now if I would like to write in this form, and if this is happening in 1 atmosphere pressure condition, so I can write Ln 2, because here also we involve 2 electron, so 2F Ln. Now we have H plus to the power 2, because we involve 2 H plus ion, and because whenever we consider, let's say AA BB equal to CC plus DD, that case we consider that AC of C to the power C, this number of moles, AD to the power D, A to the power A, this is number of moles, and AB to the power B, this is my nothing but K. We have already seen this. So now here also this power 2 would become, because 2 hydrogen ion are involved in this process, and now this is H2, because since this is gas, so it would be considered as PH2. Now this is also 1, since I am considering this is happening at 1 atmosphere pressure. Now if you consider these two reactions, this is 1, this is 2. Now we have assumed that nickel oxidation is taking place. So if nickel oxidation is taking place, that means the potential at this electrode should be having a lower value than this, because whenever we consider, that means let's say 2 electrode, we have considered that 2 electron, if it is connected with a salt bridge, this is a salt bridge and this is a solution. Now if you would like to find out which direction the current will flow, this is M1, this is M2. If current is flowing in this direction I, so electron flow is going in this direction, so this side would be anode, this side would be cathode. We have already seen this side would be cathode, this side would be anode, and electron here oxidation reaction is taking place, here reduction reaction is taking place. So now this would be, what would be the cell potential? Cell potential would be the E cathode minus E anode. So now if in this case, which is anode, where the anodic reaction happens. So this is anode and this is the cathodic reaction, this is cathodic. So we have to consider this is the cathodic region, this is the anodic region. So what would be the overall cell potential? Cell potential would be E cathode minus E anode. So now if we would like to find out what would be my cell potential, which is del E equal to minus, which would be equal to E of cathode minus E of anode, and the cathode is this and anode is this. So del E equal to E0 H plus half H2 minus E0 Ni plus Ni, simply 2 minus 1, equation number 2 minus equation number 1, plus RT 2F ln H plus whole 2. Since I have considered this is to be 1, this is to be 1, so minus ln Ni plus concentration. So this is my overall cell reaction. And what is my overall cell reaction? Ni plus H plus 2 equal to Ni plus H2. This is my overall cell reaction and this is my overall cell potential. And here also you see you have a redox reaction. The redox reaction is this to this is reduction, this to this is oxidation. So this is oxidation, this is reduction. So you have redox reaction, so this is a corrosion process. Whenever you have a redox reaction, that should be a corrosion process. Okay, now if this is the case, we know what is the value of this standard reduction potential for hydrogen, so that is 0. So this also we know, that means 0 minus 0.25 minus, because this is basically minus 0.25 plus RT 2F. Now what is the hydrogen ion concentration? Now I can write ln in the form log 2.303 log of hydrogen ion concentration into 2 to the power hydrogen concentration square minus 2.303 log Ni plus plus. Now I have to find out what is my hydrogen ion concentration. Hydrogen ion concentration can be found out from this pH. It would be equal to 8 equal to minus log hydrogen ion. So it's nothing but 10 to the power hydrogen concentration would be. So even you don't have to find out hydrogen ion concentration, because this term you can write minus it becoming plus 0.25 volt plus RT 2F into 2.303. I can put a minus sign and then I can replace it with pH. So this would be 2 pH. So 2 into pH, because I am taken minus sign. So if you take the minus sign out, so there should be a minus sign, you can write it as minus log H plus. So this is equal to minus 2 pH, because only this term, forget about these two terms. So, this term is basically minus of this term is pH. So, minus 2 pH. So, this is coming this plus minus 2.303 have taken out, so log Ni plus 2 concentration of this. So, this is my, let me just remove this. So, I can have this formula. Now, once you have this formula, so then simplify again 0.25 plus RT into 2.303 by 2F minus 2 pH minus, again minus would come. So, minus log of Ni plus 2. So, now I have to find out what is the concentration of Ni plus 2. Now, also we know Ksp for NiOH. So, Ksp solubility product should be Ni plus 2 OH minus whole 2, because Ni plus 2 plus 2 OH minus whole OH minus would be equal to NiOH whole 2. For this reaction you can write this, which is solubility product would be this. Now, what would be my concentration of OH minus? Because I know pH, from this also we can find out the concentration of OH minus. Now, again for water, H2O, H plus plus OH minus. For this I can write 14 10 to the power minus 14 would be equal to H plus OH minus. I can write this. So, if I write this, then from this I can write log of H plus plus log of OH minus would be equal to minus 14. Now, let me put a minus sign here. Let me put a minus sign here. So, this would become plus. So, this is nothing but pH. So, pH minus log of OH minus equal to 14. So, OH minus concentration would be equal to 10 to the power minus 6 unit. Let me put it as unit. Now, this is my OH minus concentration. So, let me put OH minus concentration here. So, if I put OH minus concentration here, so then my nickel ion concentration would be equal to Ksp is nothing but 1.6 into 10 to the power minus 16 divided by OH minus whole 2 equal to 1.6 into 10 to the power minus 4 unit. So, nickel ion concentration plus ion concentration in the solution I can also find out from this relation. So, if I see the nickel ion concentration here, let me put all those values here now. This, in this case, let me put, so E cell would be equal to 0.25 plus RT into 2.303 by 2F into minus sign, because here I have taken the minus sign out, into pH. So, here 2 would get cancelled. So, finally, I will have this minus log of nickel ion concentration is this. So, 1.6 into 10 to the power minus 4. So, if you simplify it, so you would get the final value del E cell would be equal to minus 0.1106. Why? Because you just put R equal to this, T equal to this, and F equal to this. So you would get this value. This is the del E cell of the reaction. Fine. So if you have this, then what would be my del G and E relation? Del G equal to minus RT minus NF E0, N is equal to 2 here. So 2F into, here is del E, and here del E is positive, negative. So these become positive. So if this becomes positive, here we should not consider del G 0 because I am not considering it in terms of in the standard state. So here it would be del G. So del G equal to a positive value. If it is positive value, then it should be non-spontaneous. Okay. So if it is non-spontaneous, that means what we have considered, that nickel will go into nickel ion and hydrogen will come out as a hydrogen gas, that assumption is wrong. So that reaction is non-spontaneous. So in fact nickel corrosion would not happen, or nickel dissolution would not happen in this condition. So we find out this relation, that is del E cell for this process. This is in gas form, and the relation what we have after considering all the concentration of nickel ion in the solution, and that is found out from solubility product, as well as the hydrogen ion concentration that is found out from pH of the solution. So we can have this relation 0.25 plus minus RT into 2.303 by 2F. So 2 will get cancelled because we have 2 pH, F into pH minus RT into 2.303 by 2F into log of 1.6 into 10 to the power minus 4. Since the nickel ion concentration we have found out this value, this much unit. So from this we can find out this is del E, we can find out this. Now at the same time, now we can find out what would be my free energy change. Free energy change del G would be minus NF, here N is 2 into del E cell. So del E cell here it is negative. So if it is negative, so there is a negative sign. So finally it would become positive. So when del G becomes positive, so that reaction is not feasible or not spontaneous. So this reaction will not happen in the condition what we have stated here. So this is a non-spontaneous process. So we can also state in another way. So if nickel ion is not forming from nickel, so then rather we can say that corrosion will not happen, the condition what we have set, that is the pH 8 deaerated water solution, and if the solubility product of nickel hydroxide is 1.6 into 10 to the power minus 16. So this is one example. So by applying the knowledge what we have gathered, the del G 0, del G, E0, E, as well as the reaction equilibrium constant, we can have all those values combined together, we can have some idea of feasibility of a reaction or the spontaneity of a reaction. Now let me again come back to reduction potential series. The reduction potential series, when we have found out, that time we have considered the values of all the reduction reaction with respect to hydrogen electrode. So if you consider all the reduction reactions, all the potential measurement with respect to hydrogen electrode, then we can have a series. This is a series where you can put all those values of standard reduction potential series from positive value to a negative value. Let us say last class we have seen, let us say this reaction Fe, let us say Ag plus E equal to Ag. This is a reduction process, and this can be E0 if this is at unit activity, and so, and this is also measured with respect to hydrogen electrode. Now we have also come to know that this is one particular value is assigned to it, that is nothing but 0 volt. So now with respect to 0 volt, if you would like to find out the reduction potential or the standard reduction potential for this reaction, they should become 0.8 volt. Similarly, you can find out what would be for copper. That case it is basically nothing but 0.34 volt. Now you can also find out for, let us say I have 0, let us say Sn tin 4 plus 2E going to Sn 2 plus. So this is also reduction process, and you have 2 ions. Now you have to maintain this 2 ion concentration unit activity. So that case you would get E0 for this reaction, and with respect to this would be equal to plus 0.15 volt. So like that way you can have a series above 0 volt or the hydrogen standard hydrogen reduction potential. Also you can have below 0 volt. So that case, let me put some value. Let me say Pb plus 2 plus 2E equal to Pb. This is also reduction reaction. That case, if you measure the potential of this reduction reaction with respect to hydrogen electrode, then you will have a value which is negative 0.13 volt. Now similar way you can find out for zinc plus 2 plus 2E equal to zinc. That case my reduction potential would be 0.761 or 761 volt. So now we have some values which are positive, we have some values which are negative compared to 0 volt. What are the importance of this minus sign and positive sign? Let us say you have two reactions that are happening. One is this reaction, another one is this reaction. So this is also considered in this form. So now if you combine these two reactions, then you can, from these values you can directly infer that this reaction, this reduction reaction would happen and this reduction reaction would not happen. And let us say I combine these two. So this reduction reaction would happen because this has a reduction potential which is positive and these are negative value. So if some reduction potential which is positive compared to the other reduction potential, and if we combine these two, then the one which has the higher reduction potential, that reduction reaction would happen, and consecutively the other reduction reaction would not happen. So this information we can have. Now from this also we can say, let us say I combine these two. In some situation I can have this reaction as well as this reaction. Now if we would like to find out or try to compare what case would be more feasible, then we can say that this value has a higher reduction potential than this. That means the silver ion would have higher tendency to get reduced and copper ion would have less tendency to get reduced. So this information we can get. So that means we can also say that this one is more active than this one. So if the reduction potential, now we can have the information what we can get, we can have which reduction process is more feasible. That means let us say if we have silver H plus plus E equal to Ag, in that case E0 Ag plus G equal to 0.8 volt, and if we have copper plus 2E equal to Cu, so that case E0 Cu plus Cu equal to 0.34. So this value is greater than this. So since this value is greater than this has higher tendency to get reduced, or that means if we from this we can easily tell that which one is more active compared to the reduction process. That means this is more active compared to reduction process. So here the deposition reaction would always take place compared to this. Now if we compare, you can also place it in this manner. So if let us say some metal M, if it has a higher tendency or the tendency to get corroded, so or metal ion formation tendency is very easy. So metal ion formation tendency is very easy. So then what we say, that the oxidation process for this metal is very high, or we can also say that this is very active metal, very active metal. So that means if the oxidation tendency is very high, then we can say that this is active metal. Now similar way, if another metal N, so that has also the tendency to form N plus ion, but there we can see that if we have this situation, if we combine these two, then always you will find that this will go and deposit on this if the reduction potential is greater than Re0 M. So now if we combine these two process, this, and if this condition is satisfied, so N plus always has the tendency to get deposited on this. Similarly, we can see that if we have zinc and copper, so in that case we have seen that if we have this situation, so always the spontaneous reaction would be zinc plus ion will form and copper will deposit. So this reaction would happen if we have a voltaic cell. In case of voltaic cell, we can have this relation, this kind of reaction. So this kind of reaction also it can be predicted from this. Now let us say this and this. So this has higher reduction potential, so it has the higher reduction ability, and this has lower reduction potential, it has a lower reduction ability. And if you combine, so in another way around, this has higher oxidation tendency than this. Sorry, this has higher oxidation tendency than this, because it has a negative value. Now if you compare these two, so this has a negative reduction potential, so it has a lower reduction ability, and if you have a lower reduction ability, it also means that it has higher oxidation ability. So zinc always will try to form zinc plus 2, and copper will always try to deposit from copper ion, and it will take 2 electron and deposit copper. So from this source we can say that which one is active and which one has a tendency to deposit. And if something has a tendency to deposit, that means it doesn't want to go into solution. If it doesn't go into solution, that we can also mention it as a nobility, or we can say that it has higher nobility or it has a lesser tendency to go into solution. So from this 0, above 0, it would always have a noble metals, and lower 0 we consider that this is active metal. So these are all the metallic system. So these are noble system and these are active system, and because we compare with respect to 0 potential, beyond 0 potential we consider as a noble metal, below 0 potential it is considered to be active metal. What does it mean? Active means it has the higher tendency to get oxidized, and noble means it has the higher tendency to get reduced. This information we get, but we cannot get many information from this. What are those information we cannot get from this? Now here we consider E0. Okay. If it is E0, that means it is a standard condition. At the same time, the activities of those ionic species may arise that the activity of those species are not 1. If these are not 1, so then we cannot say that this will, if you combine this and this, then copper and zinc, if the activities are not 1, then we cannot specifically say that zinc will corrode or zinc will form zinc plus plus and copper will deposit, copper ion will deposit in the form of copper. We cannot say that, because if we change the concentration, the actual potential on the electrode will change. Now, because let us say E Cu plus plus Cu equal to E0 Cu plus plus Cu plus RT 2F, because 2 electrons are involved here, Ln Cu plus plus Cu. Similar way, this is 1. Second case is E Cu zinc plus plus zinc equal to E0 zinc plus plus zinc plus RT 2F Ln zinc plus plus zinc. Let us say we have this relation, we have this reaction. That case, what would be my cell potential? Del E would be equal to E0 Cu plus plus Cu minus E0 zinc plus plus Zn plus RT by 2F Ln Cu plus plus Zn plus plus. Since these are 1, these are in metallic condition. Now, if you see this, if these are at unit activities, so this would always be 0.34 minus 0.76. So, it would be 0.1, this is 1.1 volt. So, this is positive. So, if this is positive, so it is a spontaneous reaction. We have seen the relation. Now, if these are not at unit activities, so if this activity is more than this, and if this value, if the value of this if Cu plus plus zinc plus plus RT by 2F, if this value is negative, if this value is negative, and let us say it values becomes 0.1.2 minus 1.2, it values, this value becomes minus 1.2. So, if it is minus 1.2, depending on the concentration of Zn plus plus and copper plus plus, so what would be my del E cell? Would be equal to minus 0.1. So, now we see that the cell potential is minus. If it is minus, then the reaction is non-spontaneous. So, this reaction would not happen, rather opposite reaction would happen. So, that case copper will come out as copper ion, zinc will deposit, zinc ion will deposit as zinc. So, that means from this we cannot predict, we cannot have any idea what would be the effect of the concentration on the cell reaction. Now, second thing is, another case is, this is always standard state. So, if we have a non-standard condition, we can also we cannot predict what would be the reaction. Or standard state means it is always considered as 25 degrees Celsius and unit activity. If it is different, the temperature is different, then we cannot predict which way it should go. Similarly, if it is alloy, let us say copper zinc alloy. In the copper zinc alloy, we cannot have the simple relation like E0 of copper and E0 of zinc, because in the alloy we are not maintaining a pure condition, because this is always with respect to the pure metal. So, these three conditions we cannot have any idea, or we cannot predict anything from this E0 or the reduction potential series. Thank you.